Okay, this is a review for test number 2 in ACE 376. If you want to study for the second test in embedded systems, a good place to go is Best of 376. This has the old homework sets and solutions for multiple semesters. And let's just go through, say, last semester's. Test number 2. Now, test 2 does not include assembler, which I know is going to be sad for everyone. It just covers C programming and controlling inputs and outputs through C. For example, the first problem from spring 2020 was turn the PIC into a 7-segment display driver. I've got 4 binary inputs and 8 binary outputs. The binary inputs represent numbers 0 through 15. And what I want to do is light up the corresponding LEDs on the output. For example, if the input is 0, I want to turn on A, B, C, D, E, F, making the number 0 appear. If the input is 7, I want to turn on A, B, C, making the number 7 appear. So the first problem is write a subroutine where I pass the number coming in, 0 through 15, and I output on port C the lights to make the 7-segment display turn on. And rather than doing all 16, just do 3. If I can do 3 numbers, I can do 16. So the requirement is when I receive this number 7, I turn on RC7, 6, 5, turn off the rest, make the number 7 appear. For 8, I likewise have this bit pattern. Now the solution, there's multiple ways of doing this. One solution is to go bit by bit, like at the bottom of the page. If I see a 7, I will just turn on RC7, turn on RC6, turn on RC5, turn off everybody else. That's perfectly valid. And do the same with the other ones. Pretty much what I found is you can do almost anything with an if statement. It may not be pretty, but it works. Second option, I could also go byte 8 bits at a time. This is a bit solution, bitwise solution. If I take the bit pattern 1110, that's hex E, 0000 is hex 0. I could also say port C equals hex E0. Or if I go to binary, 224 has this bit pattern. I could also say port C equals 224. Any of those are valid. It's pick your favorite. So one solution for this one would just be a short subroutine, void problem 1. I'll pass X. I'll then output port C is either E0, FE, E6, outputting the number 789, then return. That's typical for this type of problem. It's controlling the inputs or controlling the outputs based upon the inputs using C. Second type of problem you can expect is what we did in assembler, but now using C. Given a flowchart, write the corresponding code in C rather than assembler. For example, this one was a game show controller. I've got a host on button 0. When I ask a question and the contestants can answer, I'll hit RB0. That starts the game. And then the 2 contestants wait to hit a button. If player 1 hits the button first, port D turns on. If player 2 hits the button first, port C turns on. And I keep checking until somebody hit a button. Convert that to C. Now when doing this one, if you don't know how to do the whole code, that's okay. The way I grade this is block by block. Each block is worth 3 points, so if I don't know how to do the first 2 blocks, you can at least do the rest of them, get partial credit. To start out, to initialize, I want port B to be input. In C, that's tris B equals FF. I want port C and D to be output. That's tris C and D equals 0. And ADCON1 equals 0F. No points for that. That's just about work otherwise. This just says everybody's binary. Just a little detail for the PIC processor. This loop right here, that infinite loop, is a while loop. This says forever and ever the game plays. First thing I do is clear port C and D. I'll then check. If RB0 is 0, keep looping. That's while not RB0. I could also do while RB0 double equals 0. And as long as it's 0, I'll keep on looping. As soon as the host hits the button, RB0 goes to 1 and I kick out. I now want to check. Keep looping until somebody hits a button. And one way to do that is have a flag that's going to get set as soon as somebody hits a button. So here's a while loop. Until somebody hits a button, keep looping. If player 1 hits the button first, port D turns on and the flag is set. If player 2 hits the button, port C is set and the flag is set. Then I kick out of the while loop, and at the end I wait for the host to hit the button to start a new game. So that'd be a type where I convert the flowchart into C code. Third type of problem you can expect is we have analog inputs. With analog inputs, the A to D reads between 0 and 1023. With that, I can change how the program runs. For example, here, I want to build a trombone that goes from 220 Hz to 440 Hz as the A to D goes from 0 to 1023. And it's also given that if I count to 1000, I play 300 Hz. So what I want to do is modify this code, change that number 1000 based upon the A to D reading. And what I want to change it to is proportional. So if 1000 counts gives me 300 Hz, 1363 counts gives me 220. It's proportional. 300 Hz goes to 220 Hz. For the frequency to get longer, the period gets longer. Actually, for the frequency to go down, the period goes up. The period is what the count is. To get a longer period, I need a higher count. So pick the ratio that's bigger than 1, 1363. If the frequency goes up, the period gets shorter. So I need a number less than 1000. 440 Hz will be 681. Now do a linear curve fit. When A to D is 0, I want 1363. When the A to D is 1023, I want 681. So there's my curve fit. Now modify the code, add this line. Based upon the A to D reading, I'll change n. Then instead of counting to 1000, I'll count to n. That way you should get between 220 Hz and 440 Hz as I change the A to D. It won't be exactly right because this line of code has been added to the loop. If I change the loop, I change the timing. But for what we know now, that's about all you can do. Another type of analog input is the analog input can be used as a sensor. If I have a temperature sensor, the resistance changes with temperature, put that in voltage divider. As resistance changes, voltage changes, and the voltage I can read with the analog input. So if I read the number 300, the voltage will be 300 at a full scale, 300 at 1023 times 5 volts, gives you 1.466 volts. By voltage division, this voltage is R over R plus 3000. Solving backwards, R is 1244 ohms. Then plugging it into here, the temperature is 293 Kelvin, or 20 Celsius. You'll also have a question on the Chisquare test and t-test. For Chisquare test, I'll give you the data. For example, in this one, I flip a coin 20 times, I get 14 heads. Is it a fair coin? To do that, I set up a Chisquare table. The expected number, or expected frequency is 10. I should get 10 heads and 10 tails. I actually got 14 and 6. The chi-squared score is the difference between the expected and actual squared divided by expected. Add them all up, I get a chi-squared score of 3.2. Now you can use StatTrack or table. I'll give you a table on the test as well. I've got 2 bins, meaning 1 degree freedom. The number I want is a chi-squared score of 3.2. So look in here to find 3.2, and it's between 90 and 95%. It's closer to 95, so it's right around 93. Or you could use StatTrack and get 93% as well. So 93% chance this is a loaded die, or loaded coin. And t-test, I'll give you something like this. Here's the data, here's the mean, here's the standard deviation, here's the sample size. Now start analyzing it. This problem was, this is the point spread for NDSU in 2019 for their football games. NDSU won by 8 points, 28 points, 6 points, won by 24 points, and so on. What's the probability NDSU will win its next game? To do that, I set up a t-score. What is the difference between the mean and 0? Because if the point spread is negative, NDSU lost. Divided by the standard deviation. So 0 is 2.158 standard deviations away from the mean. To convert that to a probability, I go to a t-table. I have 15 games, meaning 14 degrees of freedom. I look down here on the t-table at 14 degrees of freedom. And 2.15, fortunately is on the t-table, means 2.5%. So there's a 2.5% chance that NDSU will either win or lose its next game. The point spread is positive. NDSU's been winning, so that means it's actually 97.5% chance they'll win, 2.5% chance they'll lose. The second question was, what's the confidence interval for the point spread? If we have a 95% confidence interval, each tail is 2.5%. So go on the table for 2.5%, 14 degrees of freedom, sample size of 15, and the t-score is 2.15. So I want to go left and right 2.15 standard deviations. So take the mean minus 2.15 standard deviations, mean plus 2.15 standard deviations, and here I misspelled plus. And I get a point spread between 0.26 and 52. So it's 95% certain that NDSU will win the next game by somewhere between 0.26 points and 52 points. That's kind of what you can expect for test number 2 and 376, some statistics and some C programming.